The MiG-21 pilot eases his throttle forward over the Red River Valley, eyes scanning the afternoon haze for contrails. His RP-21 Sapfir radar sweeps the sky ahead in steady pulses, painting returns on the small scope mounted between his knees. Standard intercept procedure. Let the radar find them first, close to visual range, then engage. The North Vietnamese Air Force has perfected this dance over 3 years of combat. Ground control vectors him northwest toward reported American strike packages. His wingman holds formation 500 meters back. The radar continues its methodical scan pattern exactly as Soviet instructors taught at Krasnodar. 10-degree sweeps, pulse repetition frequency locked at 3000 Hz, search mode active. He's hunting F-4 Phantoms returning from targets near Hanoi. 60 miles south, Lieutenant Colonel Robert Lodge rolls his F-4D Phantom into a gentle turn. His backseater, Captain Roger Locker, watches a small Bach mounted beside the radar warning receiver. A green indicator light pulses in rhythm, steady, predictable. Every sweep cycle identical. The frequency readout shows 3000 Hz. "Bandits, you're 11 o'clock, 53 miles, Locker calls over intercom. Lodge can't see anything through the canopy except blue sky and distant clouds. Their own APQ-120 radar isn't even powered up yet. Ground control hasn't called any threats. But that little box, the ALR-46 radar homing and warning system, is tracking 2 Soviet-made fire control radars painting their distinct electronic signature across the stratosphere. The MiG pilot checks his fuel state. His radar shows empty sky. The Americans must be lower, masked by ground return. He adjusts his scan angle downward, increasing pulse power. Each emission travels outward at the speed of light. A precisely timed radio wave designed to bounce off enemy aircraft and return to his receiver. What Soviet engineers never anticipated was how that same emission would propagate far beyond its useful range, carrying a fingerprint as unique as a voice. The RP-21's pulse width, repetition rate, frequency stability, and scan pattern create an electromagnetic signature that specialized receivers can detect at ranges where the radar itself remains useless for tracking. Lodge descends to 15,000 feet, maintaining his turn to keep the threat bearing steady off his nose. The ALR-46 display updates continuously. Range decreasing, signal strength building. 47 miles now, still 11 o'clock, Locker reports. They're positioning for an intercept the North Vietnamese pilot doesn't know is happening. The technology in that small black box represents 18 months of rushed development, field testing, and combat refinement. It's adapting missile warning receiver components to detect the specific characteristics of Soviet fire control radars, exploiting physics the designers in Gorky never considered when they prioritized detection range over emission security. The MiG pilot's radar finally paints a return. 2 contacts, low, heading south. He alerts his wingman and begins a descent vector for visual identification. His radar increases scan rate automatically as range closes, pumping more pulses into the air, each one announcing his exact position to the specialized receiver that's been tracking him for the last 5 minutes. He expects the Americans to react when his radar locks them up. He expects ground control to vector him into position. He expects the engagement to begin when he achieves visual contact at 3 miles. What he cannot expect, because nobody has briefed this possibility, is that the Americans have been watching his approach since he was beyond the horizon, using his own radar against him like a searchlight in darkness. Lodge pulls his Phantom into a climbing left turn, positioning the sun behind his aircraft. The ALR-46 box shows both contacts now at 38 miles, descending through his altitude. Locker reads the tactical geometry. The MiGs are setting up for a classic tail chase, expecting to find F-4s running south toward their tanker tracks. "They're coming down to us," he announces. Lodge arms his AIM-7 Sparrows and powers up the APQ-120. The Americans will meet these interceptors head-on, not fleeing south as doctrine predicts. The North Vietnamese pilots have no idea their careful approach has been transparent for the last 7 minutes. April 10, 1972. The engagement unfolds exactly as 4 other intercepts have this week. F-4 crews calling out MiG positions before Red Crown radar controllers, before visual contact, before the geometry makes any conventional sense. At Udorn Air Base in Thailand, intelligence officers review mission tapes with growing confusion. Pilots are reporting threat bearings and ranges that shouldn't be possible without ground-controlled intercept vectors. The Phantoms aren't carrying new radars. Their APQ-120 systems have the same 45-mile maximum detection range they've always had. And that's against non-maneuvering targets in ideal conditions. Yet crews are maneuvering against threats at 50-plus miles with confidence that suggests solid tracking data. The MiG pilot levels at 12,000 feet. His radar shows the contacts ahead, still heading south. Predictable Americans running for safety. He signals his wingman to spread formation for the attack run. His pulse repetition frequency shifts slightly as the radar transitions from search to track mode, the emission pattern changing from broad sweeps to focused illumination. 60 miles away at Hanoi's Gia Lam airfield, Soviet advisors monitor the engagement through encrypted radio links. Their Vietnamese students are executing the intercept perfectly. Early radar detection, controlled descent, tactical formation spacing. The RP-21 radar is performing exactly to specifications. 22 miles. Lodge rolls level, pointing directly at the threat bearing. His own radar finally paints both contacts. 2 solid returns at 21 miles, slightly high. "Judy," he calls, taking control of the intercept from ground controllers who still haven't called the bandits. The ALR-46 has given him a 3-minute advantage, enough time to position his Phantom for a frontal quarter shot instead of a desperate defensive engagement. Locker watches the green pulse on the detector display quicken as the MiG's radar shifts modes. He's tracking now, probably locked. The words carry no alarm. They've known this MiG's position since it was beyond visual horizon. The Vietnamese pilot sees the impossible. The F-4 is turning toward him, climbing, nose pointed directly at his position. The Americans are reacting to his presence before visual range, before his radar lock should have alerted their warning receivers. He checks his equipment. The RP-21 shows normal operation, no faults, standard search pattern until 30 seconds ago. His wingman confirms identical readings. The Soviet advisors listening to encrypted radio traffic hear confusion in the pilot's voice. Standard intercept geometry has collapsed. The hunters have somehow become visible to their prey at ranges where detection should be physically impossible given known American radar capabilities. Lodge fires 2 AEM-7E Sparrows at 18 miles. The MiG pilot sees missile plumes and breaks hard left, diving away from the threat. His radar warning receiver screams. He's being illuminated by the F-4's fire control radar now, which makes sense. What makes no sense is how the Americans positioned for this shot, how they knew where to point their aircraft 3 minutes before radar contact should have occurred. The Sparrows miss in the defensive break, but the engagement is already lost. The Americans owned this intercept from the moment his RP-21 began searching empty sky. Colonel Toombs sits in the operations room at Noi Bai Air Base, reviewing engagement reports with 2 Soviet advisors. 5 intercepts in 8 days have followed the same pattern. F-4 crews positioning defensively before Vietnamese pilots achieve radar lock, before visual contact, sometimes before ground control even calls the threats. The Americans are reacting to MiG presence at ranges that violate every known performance parameter. The Soviet officers examine equipment logs from the RP-21 radars. Every system shows nominal operation. Pulse repetition frequency stable at 3,000 Hz. Search patterns executing normally. No faults, no anomalies, no electromagnetic interference that would explain how the Americans are detecting aircraft at 50-mile ranges. They have new ground radars, one advisor suggests, pointing at a map of the Red River Valley. The Americans operate EC-121 airborne early warning aircraft over the Gulf of Tonkin, along with Navy ships equipped with search radars. Perhaps upgraded systems are feeding positional data to F-4 crews with unprecedented accuracy. But the timeline doesn't support this theory. The intercepts are happening too fast, with the Phantoms maneuvering immediately on threat bearings without the communication delays that ground-controlled intercepts require. Pilots are calling MiG positions before Red Crown controllers, which means the data is coming from onboard systems. Vietnamese pilots debrief in separate rooms. Each describes identical tactical situations, standard search radar procedures, normal approach vectors, then sudden American awareness at impossible ranges. One pilot, a 5-year veteran, describes his RP-21 operating perfectly throughout the engagement. He followed Soviet doctrine precisely. Activate search radar at maximum range, maintain scan pattern until visual contact, then transition to track mode for weapons employment. The Americans responded to his presence at 43 miles. His radar couldn't detect targets reliably beyond 35 miles, even under ideal conditions. The physics don't reconcile. Security officers investigate ground personnel. Perhaps American intelligence has infiltrated the maintenance crews, sabotaging radar systems to emit tracking signals. They inspect RP-21 units removed from aircraft, testing each component against factory specifications. Soviet technicians from the Gorky radar plant verify the equipment matches design parameters exactly. The radars are performing as built. No modifications, no additional transmitters, no hardware that would explain American detection capability. The investigation expands to communication security. Maybe the Americans are intercepting radio traffic, using ground control vectors to predict MiG positions. But the intercepts are happening before Vietnamese controllers issue vectors, sometimes before the MiGs even check in on tactical frequencies. Soviet advisors draft classified reports for Moscow. The Americans have achieved a detection capability that shouldn't exist given known technology. The F-4's APQ-120 radar lacks the range. Ground-based systems lack the geometry. Infrared sensors can't work at these distances. The reports list 3 possibilities: revolutionary new radar technology, classified spy satellite data being fed directly to cockpits, or some form of signal intelligence breakthrough. None of the theories satisfy the observed tactical behavior. Moscow's response arrives within 4 days. Continue normal operations, assume American technical breakthrough, do not modify equipment or doctrine without further analysis. At Gia Lam Airfield, maintenance crews perform diagnostic tests on RP-21 systems, measuring every emission parameter. The radars transmit at exactly 3,000 Hz pulse repetition frequency during search mode. The pulse width measures 2.5 microseconds. The scan pattern executes a 10-degree sweep every 1.2 seconds. Every measurement matches Soviet specifications. What nobody considers, because the concept exists outside their operational framework, is that these perfectly normal emissions are propagating far beyond the radar's useful detection range, carrying the RP-21's unique signature like a radio beacon. The Vietnamese are searching for sabotage in their equipment when the vulnerability is fundamental to the radar's design, a side effect of prioritizing detection performance over emission security. Jack Donovan stands in Applied Technology Incorporated's workshop in Palo Alto, measuring the electromagnetic signature from a captured RP-21 Sapfir radar unit. The year is 1967. The radar sits on a wooden test bench, powered by a diesel generator that makes the corrugated metal building shake. Donovan isn't a physicist. He's an electrical engineer who spent the last 3 years designing missile warning receivers for Air Force contracts. The RP-21 arrived 2 weeks ago via CIA channels, pulled from a defector's MiG-21 that landed in Israel during the Six-Day War. His assignment is simple: characterize the radar's emissions for threat warning systems. The spectrum analyzer shows something unexpected. The RP-21's pulse repetition frequency holds rock steady at 3,000 Hz with less than 5 Hz variation. Most radars drift 10 to 15 Hz as components heat up during operation. This Soviet design maintains frequency stability that American engineers would consider over-engineered for a fighter radar. Donovan adjusts the analyzer's sensitivity, measuring the pulse shape. Every emission carries identical characteristics: 2.5 microsecond pulse width, sharp rising edge, clean fall time. The consistency is remarkable. It's also exploitable. He sketches the concept on yellow legal paper that evening. The ALR-46 missile warning receiver currently equips F-4 Phantoms to detect SA-2 surface-to-air missile radars. The system uses crystal video receivers tuned to specific frequency bands, comparing pulse characteristics against a library of known threats. Donovan's insight is that Soviet fire control radars emit signatures just as distinctive as SAM systems, but at much higher duty cycles. The RP-21 pumps out 3,600 pulses per second during search mode, each one announcing the radar's presence at ranges far beyond where the radar itself can detect targets. A modified ALR-46 could detect these emissions at 60-plus miles, double the RP-21's useful range. Applied Technology receives a contract in October 1967 to develop the modification. The timeline is aggressive: 6 months to prototype, another 6 for flight testing. Donovan's team pulls ALR-46 components and adds signal processing that discriminates between different Soviet radar types. The RP-21 becomes Priority 1 because MiG-21s represent the primary air-to-air threat over North Vietnam. The engineers program the system to recognize the 3,000 Hz PRF, the specific pulse width, and the scan rate. The modified receiver provides bearing, approximate range based on signal strength, and threat identification. Flight testing begins at Eglin Air Force Base in April 1968. A T-39 Sabreliner carries the prototype system, while F-4 Phantoms simulate MiG-21 radar emissions, using captured RP-21 units mounted on test stands. The detection ranges exceed predictions. The modified ALR-46 tracks the simulated threat radar at 72 miles under clear conditions. Signal strength correlates reliably with range, giving crews a tactical picture that transforms intercept geometry. The system adds 3 pounds to the F-4's equipment bay and requires no cockpit modifications beyond a small display panel. Production authorization comes in September 1968, but integration moves slowly through Air Force bureaucracy. The Vietnam War's air combat dynamics are shifting. Operation Rolling Thunder ended in November 1968, reducing the urgency for new air-to-air systems. The modified ALR-46 units sit in storage at Warner Robins Air Logistics Complex for 3 years. Donovan moves on to other contracts, assuming his radar detection concept has been shelved indefinitely. Then North Vietnam launches the Easter Offensive in March 1972. American air operations resume at full intensity. Somebody at Tactical Air Command remembers the modified ALR-46 units collecting dust in Georgia. Rush orders go out to install the systems in F-4D Phantoms deploying to Southeast Asia. Donovan's 5-year-old concept finally enters combat, exploiting a vulnerability Soviet engineers still don't know exists. The physics of radar betrayal begins with pulse repetition frequency. The RP-21 Sapfir radar transmits 3,000 pulses every second during search mode, each pulse a burst of electromagnetic energy at 9.5 GHz. The radar needs this high pulse rate to scan a 60-degree azimuth sector while maintaining target illumination long enough for return signals to register. Soviet engineers at the Gorky plant designed the system for maximum detection performance. The 3,000 Hz PRF represents the optimal balance between range resolution and scan rate for a lightweight fighter radar. What they didn't account for was how those 3,000 pulses per second would propagate beyond the radar's useful detection range. Radar detection follows inverse square law physics. The transmitted pulse travels outward, hits a target, and reflects back to the receiver. The signal strength decreases with the square of the distance twice, once outbound, once on the return trip. This physical reality limits the RP-21's effective range to roughly 35 miles against fighter-sized targets. Beyond that distance, return signals fall below the receiver's sensitivity threshold. But the outbound pulse continues traveling at the speed of light, carrying full signal strength in a constantly expanding sphere. At 60 miles, the pulse is too weak to produce a usable return echo, but it's still strong enough to trigger a sensitive receiver designed to detect that specific signal. The ALR-46 modification exploits this asymmetry. Donovan's team tuned crystal video receivers to 9.5 GHz with narrow bandpass filters that reject everything except signals matching the RP-21's exact characteristics. The system measures pulse width to discriminate between Soviet radar types. The RP-21's 2.5 microsecond pulse differs from the MiG-19's older RP-9 radar, which transmits 4.0 microsecond pulses at 2,400 Hz PRF. This signal fingerprinting allows the ALR-46 to identify specific threat types and display the information to F-4 crews as distinct warning tones and indicator lights. Range estimation uses received signal strength. The ALR-46 measures the amplitude of incoming pulses and compares them against calibration curves developed during flight testing. A strong signal indicates close range. Weak signals mean distant threats. The system provides approximate range in 5-mile increments, accurate enough for tactical decision-making, but imprecise compared to true radar tracking. Bearing accuracy is better, using a 4-antenna array mounted around the F-4's fuselage to triangulate signal direction within 2 degrees. The crew sees a small display showing threat bearing, approximate range, and radar type identification. The scan pattern provides additional intelligence. The RP-21 executes a repetitive 10-degree sweep every 1.2 seconds, creating a predictable rhythm in the received signal. When the radar antenna points directly at the F-4, signal strength peaks. As the antenna scans past, the signal fades. This pulsing effect happens at 0.83 Hz, the scan rate, and allows the ALR-46 to distinguish between being tracked and simply being inside the radar's search volume. When the RP-21 transitions from search to track mode, the scan pattern tightens and the update rate increases. The ALR-46 detects this change and alerts the crew that they've been designated as a target. Soviet doctrine never emphasized emission control because radar warning receivers were designed to detect missile guidance systems, not search radars. The RP-21's designers optimized for detection range and tracking accuracy, assuming the radar's emissions would only matter at ranges where engagement was imminent. This assumption held true against early missile warning receivers with limited sensitivity and no signal processing capability. Donovan's modification changed the equation by turning the RP-21's strengths, frequency stability, high pulse rate, consistent characteristics, into vulnerabilities. Every pulse the radar transmitted became a homing beacon for American receivers. The first modified ALR-46 systems arrive at Ubon Royal Thai Air Force Base in May 1972, packed in foam-lined cases marked with red priority tags. Technical representatives from Applied Technology Incorporated fly in to supervise installation on F-4D Phantoms from the 8th Tactical Fighter Wing. The mechanics worked through 2 nights, removing standard ALR-46 units and replacing them with the enhanced systems. Each installation takes 6 hours, mounting the modified receiver box, routing antenna cables to 4 new fuselage-mounted pickups, connecting the display panel beside the existing radar warning equipment. By May 8th, 12 Phantoms carry the upgrade. Crews receive a single briefing. The new system detects enemy fire control radars at extended range, provides bearing and approximate distance. Listen for the audio tone. Captain Richard Steve Ritchie flies his first mission with the modified system on May 10th. His backseater, Captain Charles de Bellevue, monitors the new display during a MiG-cap patrol over the Red River Delta. At 14:20 hours, a green indicator light pulses on the panel. The audio tone chirps in rhythm with the light, steady, predictable, the characteristic signature of an RP-21 in search mode. De Bellevue reads the bearing. Bandits, 1 o'clock, range shows 40-plus miles. Ritchie can see nothing but haze. Red Crown hasn't called any threats. Their APQ-120 radar shows empty sky. But that little green light is pulsing with confidence that something is out there, radiating 3,000 times per second. Ritchie turns 10 degrees right to put the threat bearing on his nose. The signal strength indicator creeps upward as range decreases. De Bellevue watches the display update. 38 miles now, still 1 o'clock, steady bearing. They're closing head-on with something that doesn't know it's being tracked. The RP-21's emissions are painting a perfect picture of its own position, while its operator searches empty sky, waiting for targets to appear in his useful detection range. The Americans own this intercept geometry before the merge even begins. The tactical advantage is absolute. Traditional intercepts require ground-controlled vectors or random visual acquisition. Both methods give the enemy parity in initial detection. The modified ALR-46 breaks this symmetry by exploiting the enemy's own sensors. MiG pilots operating under Soviet doctrine activate their radars early, trusting that detection at maximum range provides first-shot advantage. This assumption held true until American receivers learned to see those radar emissions from twice as far away. Now every MiG-21 that powers up its RP-21 announces its presence like a lighthouse, giving F-4 crews 3 to 5 minutes of preparation time. Lodge and Locker score their kills on May 10th, using the system exactly as designed. They detect 2 MiG-21s at 51 miles, position for a head-on intercept, and fire AEM-7 Sparrows at 18 miles. One MiG goes down, the other breaks off. 2 days later, Ritchie and de Bellevue use the same tactical sequence to down their first MiG-21. The modified ALR-46 detects the threat at 47 miles. They maneuver for position, shoot at 21 miles. The pattern repeats throughout May and June as more F-4Ds receive the upgrade. The 8th Tactical Fighter Wing's intelligence officers track the results. In the first 30 days of linebacker operations, F-4 crews with modified ALR-46 systems account for 11 MiG-21 kills with 0 losses in those specific engagements. The Vietnamese are still flying Soviet doctrine. Activate radar early, close to visual range, engage. Every intercept begins the same way. The RP-21 starts searching. The ALR-46 detects it. The Americans position for advantage. The North Vietnamese don't yet understand why their carefully planned intercepts keep dissolving into defensive engagements against phantoms that somehow knew they were coming. The pattern breaks on July 8th. Captain Ritchie and de Bellevue patrol the Red River Valley expecting the standard engagement sequence: early ALR-46 detection, controlled intercept geometry, radar-guided missile shot. The modified system shows nothing. Their APQ-120 radar sweeps empty sky. Red Crown calls bandits in the area but provides no vectors. Then, at 4 miles, a MiG-21 flashes past their canopy, invisible until visual range. The Vietnamese pilot never activated his RP-21 radar. He approached using ground-controlled vectors alone, accepted the tactical disadvantage of no onboard radar picture, and nearly achieved a gun solution before the Americans spotted him. North Vietnamese Air Force Headquarters issued the directive 3 weeks earlier, after analyzing 37 MiG losses between April and June. The order is specific: minimize RP-21 usage during intercepts, rely on ground control for vectors, activate radar only inside visual range when weapon employment is imminent. Soviet advisors object. The directive contradicts fundamental principles of beyond visual range engagement. The RP-21 exists to provide early detection and tracking. Shutting it down renders the MiG-21's primary sensor useless, reducing the aircraft to a visual-only fighter with performance inferior to the F-4 in most regimes. The Vietnamese commanders are adamant. Something is allowing the Americans to detect MiG presence at impossible ranges. Until the mechanism is identified, radar emissions must be restricted. The tactical consequences are immediate. MiG-21 pilots lose their standoff detection capability, forced to close to 3-mile visual range before knowing enemy positions with certainty. Ground controllers vector them toward American formations, but the geometry is imprecise compared to onboard radar tracking. The pilots accept this disadvantage because survival requires it. Between July 10th and August 15th, only 2 MiG-21s are lost in air combat. F-4 crews report frustration. The modified ALR-46 systems show no contacts. The early warning advantage has vanished. The Vietnamese have adapted without understanding the specific vulnerability they're mitigating. Soviet technical teams at Noi Bai finally suspect the truth in mid-August. A signals intelligence officer reviews emission logs and engagement timelines, noting the correlation between RP-21 activation range and American response timing. He drafts a classified assessment. The Americans have developed receivers capable of detecting Soviet fire control radars at extended range, using the radar's own emissions for targeting. The assessment reaches Moscow within a week. The response is silence. Admitting the vulnerability would require acknowledging a fundamental design flaw in the RP-21, and by extension, similar radars equipping Soviet forces worldwide. The emission characteristics that make the RP-21 detectable, frequency stability, high pulse rate, predictable scan patterns, are intrinsic to its operation. Fixing the problem would require complete redesign. The North Vietnamese maintain their restricted radar doctrine for the remainder of the war. Pilots train for visual intercepts, accepting reduced combat effectiveness in exchange for survival. The tactical adjustment works. MiG losses decrease dramatically, even as American air operations intensify through late 1972. But the cost is strategic. The MiG-21's beyond visual range capability, the feature that made it competitive with American fighters, becomes unusable in contested airspace. The Vietnamese are flying a $1.2 million interceptor as if it were a 1950s-era day fighter. American intelligence never learns the full details of the Vietnamese countermeasure doctrine. The modified ALR-46 simply stops producing contacts with the same frequency. Some analysts attribute this to reduced MiG sortie rates. Others suspect the Vietnamese have modified their tactics but can't identify the specific change. The truth, that North Vietnam abandoned a core element of Soviet doctrine to counter an American technical advantage, remains classified in Hanoi's military archives. The RP-21 radars continue operating normally on the ground during testing. Soviet advisors never confirmed the emission vulnerability in official channels. The modified ALR-46 data feeds into a larger program at Wright-Patterson Air Force Base in late 1972. Engineers from the avionics laboratory examine combat reports, signal intelligence logs, and technical debriefs from crews who use the system. The tactical value is undeniable. Early threat detection transformed intercept geometry in every engagement where MiG pilots operated their radars conventionally. But the implementation is crude. The system provides bearing and approximate range through signal strength estimation, but it can't discriminate between multiple emitters at similar bearings. The display shows a single threat indication when 2 MiG-21s fly in formation. Range accuracy degrades beyond 50 miles as signal strength measurements become unreliable. Captain Paul Dingman leads the development team for what becomes the ALR-67 radar warning receiver. The requirement emerges from linebacker combat experience. Provide comprehensive threat warning against both surface-to-air missiles and airborne radars, with precise bearing information, threat identification, and multiple target handling. Dingman's team starts with a modified ALR-46 concept, but rebuilds the signal processing from first principles. The new system uses 4 antennas with individual receivers, allowing precise triangulation through phase comparison. A digital processor compares incoming signals against a library of 128 different threat types, identifying radars by their pulse characteristics and displaying them as distinct symbols on a cockpit screen. The ALR-67 enters service in 1975, too late for Vietnam, but in time to establish the template for all subsequent radar warning receivers. The system can track 16 separate threats simultaneously, providing bearing within 1 degree and threat type identification within 0.3 seconds of detection. Soviet fire control radars remain the primary air-to-air targets. The RP-21 signature library expands to include the MiG-23 Sapfir 23, the MiG-25's RP-25, and updated versions of older systems. Each radar's emission characteristics become a liability in the new electromagnetic environment. The technology forces a fundamental shift in fighter doctrine. By 1980, every NATO and Warsaw Pact fighter carries some form of radar warning receiver capable of detecting enemy fire control radars at extended range. The tactical advantage that American crews enjoyed in 1972, knowing enemy positions before the enemy knew theirs, becomes symmetrical. Soviet pilots receive the same capability, exploiting the same physics against American APG-63 and APG-66 radars. The electromagnetic spectrum becomes contested territory where every emission carries risk. Emissions control doctrine emerges as the countermeasure. Fighter pilots learn to delay radar activation until weapon employment is imminent, accepting reduced situational awareness in exchange for reduced detectability. The F-15's APG-63 radar can detect targets at 60-plus miles, but turning it on at maximum range announces the fighter's presence to enemy warning receivers at even greater distances. Pilots develop techniques for brief radar snapshots, powering up for 2-second scans, then going silent while processing the information. The radar becomes a tool to be used sparingly rather than continuously, fundamentally changing how fighters operate in contested airspace. Low probability of intercept radar technology follows directly from this arms race. Engineers develop frequency-agile radars that change operating frequency thousands of times per second, making signal detection and identification difficult. Pulse compression techniques allow radars to achieve range resolution without high peak power that warning receivers can detect easily. By 1990, the F-22's APG-77 radar uses active electronically scanned array technology with emission patterns designed specifically to minimize detectability. The direct descendant of lessons learned when Jack Donovan measured a captured RP-21's emissions in a Palo Alto workshop 23 years earlier. The vulnerability he exploited became the defining characteristic of modern radar design. Emissions management matters as much as detection performance. The ALR-46 modification established a principle that governs air combat 50 years later. Sensors become liabilities in contested electromagnetic environments. The RP-21 Sapfir radar represented Soviet engineering excellence in 1965. Stable frequency control, high pulse rate, consistent performance characteristics that maximize detection capability. These same features made it detectable at twice its useful range. Once American engineers understood the physics of one-way signal propagation. The 3,000 pulses per second that enabled effective target tracking became 3,000 opportunities per second for enemy receivers to fix the radar's position. Stealth technology development accelerates directly from this realization. Lockheed's Have Blue program, which leads to the F-117 in 1981, prioritizes radar cross-section reduction to minimize the range at which enemy radars can detect the aircraft. But designers recognize that passive detection through radar warning receivers makes emissions from the aircraft's own sensors equally dangerous. The F-117 carries no radar at all. Navigation and targeting rely on infrared systems and GPS coordinates to avoid electromagnetic emissions. The aircraft becomes invisible by refusing to illuminate itself. The principle extends beyond aviation. Naval vessels adopt emissions control procedures that restrict radar use during operations near hostile forces. The Aegis combat system can track hundreds of targets simultaneously using the SPY-1 phased array radar. But that capability comes at the cost of announcing the ship's position to any receiver within 200 miles. Modern doctrine balances surveillance requirements against detectability risks, using radars in controlled bursts rather than continuous operation. Submarine warfare embraces the concept completely. Passive sonar remains the primary sensor, specifically because active sonar pulses reveal the submarine's position to anyone listening. Low probability of intercept technology becomes the engineering solution. Modern radars use spread spectrum techniques that distribute transmitted energy across wide frequency ranges, making individual pulses difficult to detect above background noise. The F-35's APG-81 radar can adjust its emission patterns in real time, using just enough power for target detection while minimizing the signal strength that reaches enemy warning receivers. Frequency hopping occurs thousands of times per second, preventing receivers from locking onto a stable signature. These techniques add enormous complexity to radar design, but become mandatory for survival in environments where enemy warning systems can detect conventional radar emissions at ranges measured in hundreds of miles. Electronic warfare evolves into a continuous cycle of adaptation. The ALR-46 modification exploited the RP-21's predictable characteristics. Soviet engineers responded by developing frequency-agile radars with variable pulse patterns. American systems adapted with wider bandwidth receivers and more sophisticated signal processing. Each generation of radar warning receivers forces corresponding changes in radar design, pushing both technologies toward greater complexity. Modern systems routinely process emissions across frequency ranges from 2 to 18 GHz, identifying threats by subtle differences in pulse timing measured in nanoseconds. The human cost of Donovan's discovery never appears in technical specifications. Those 37 MiG-21s lost between April and June 1972 carried pilots who trusted their equipment, followed their doctrine, and died because their radars betrayed them. The modified ALR-46 transformed tactical geometry so completely that Vietnamese pilots flying capable aircraft with competent training found themselves outmatched by physics they couldn't see. Their countermeasure, shutting down radars and accepting visual-only intercepts, acknowledged defeat in the electromagnetic domain while preserving lives. 60 miles over the Red River Valley in spring 1972, that green light pulsing on the ALR-46 display represented more than tactical advantage. It marked the moment when radar emissions became tactical liabilities, when sensors designed to provide information instead provided targeting data to the enemy. Every fighter radar, every fire control system, every electromagnetic sensor operating today inherits this legacy. The knowledge that searching for enemies makes you visible to anyone listening,